Jai Hind all of you. Myself Nishu Bansal from CSC department. Welcome to the next lecture series of the image processing KCS 062. It is being taught in the 6th sem. Let's see the content of today's presentation. That is, the first topic we will cover is the histogram equalization. Then we will see the spatial domain image filtering. In that we will see in two domains, that is the smoothing and the sharpening filtering. This we have seen in the intensity enhancement also, that we do the intensity enhancement in two domains, that is the spatial domain and the frequency domain. In this particular lecture, we will see the spatial domain. So let's first start with the histogram equalization. So basically when we talk about the histogram processing, the main purpose of creating the histogram is, it is based upon the two things, that is the input is the RK, where RK is the intensity values, that is for say we have a image, each image has x comma y coordinates and we divide the image into this is particularly a 2D image. So this f of x comma y is nothing but this is the intensity value RK. Okay, the range, for say the range of intensity values, it is taking from 0 to 2 ki power some value, that is k. So this particular RK is the kth intensity value, that is it can be any values from 0 to 2 ki power k. Now this particular thing RK, the intensity values, it may be taken by more than 1 pixels. For say this particular image has the value 0, 1, 2, 0, 1, 1, 0, 2, 2, 1, 0, 0, 1, 1, 2, 1, 3, 4, 5, 1, 2, 0, 0, 0, 0. Now for say RK, the kth intensity value, that is R of 0 we have is the 0 value for say. Now N of K, N of 0, that is number of pixels having the 0 intensity value. So the number of pixels are 0, 1, 2, 3, 4, 5, 6, 7, 8. So N naught would take the value 8. That is, there are n number of pixels having the 0 intensity value. Now histogram, it would be, we represents R of K, it is a function of R of K, that for a given intensity value, how many pixels are taking that particular intensity value. So normalized histogram, here what we do is, we create a probability, we find the probability of R of K. The probability of any intensity value, that would be equal to number of pixels, that is NK, NK divided by total pixels in the screen. So if my screen is having m number of rows and n number of columns, so then the normalized histogram probability would be equal to NK upon Mn. That is, this would be the probability of the kth intensity value. So let's see why we need the histogram equalization. As you can see in the first image, the image is more on a darker side. That is the intensity values, here we can see that blackish intensity value. So we know that we give the lower intensity values for say 0, around 0, we give it to the black color in a particular grayscale image. And higher intensity values for say 256, we give it to the whiter shade or a lighter image value, lighter pixel, that would get the value 256. So here more, if we grow the histogram for this, we can see that the histogram is more inclined towards a lower intensity value. So here if we see a lighter image, that is which has more whitish color pixels, here the intensities or the histogram, if we plot, we can see that it is more inclined towards the right side, to the higher side of the intensity values. Now if we see a very low contrast image, that is we are not able to distinguish the foreground from the background. Almost the color combination of both foreground and the background is almost, it's not quite good contrast. So it's a very low contrast image. So here particularly the histogram would be more in the middle. So neither it would be in the lower side nor it would be in the higher side. Now if we see a very good contrast image where we can distinguish the foreground objects from the background objects clearly. Such kind of image is a image with a good contrast or a high contrast image. If we look at the histogram for this kind of image, we can see that it would be almost equally distributed, or it would be covering almost all the intensity values which are in the grayscale image. So this is the good quality image, we can say. So our idea through the histogram equalization is to achieve a image of this kind of quality. So let's see the concept behind how we apply the histogram equalization. So along the x-axis we have is R is the input intensity, that is before the transformation or before applying the histogram equalization. So it takes a value from 0 to L minus 1 is the maximum intensity value that a pixel can take. Then along the y-axis we have is the probability, that is for each pixel intensity value, how many pixels are taking that particular intensity value. So I told you how we can find the probability also. So probability is nothing but the number of pixels taking that particular intensity value divided by total number of pixels. So if we look at the graph, it would be like this somewhat. It's not equally distributed along all the intensity values. So the maximum can be that this is the peak, we denote it by capital A. So we need to transform it applying histogram equalization. Idea is to get a uniform distribution of intensity values along all the pixels. So here we want to achieve, that is, it's not that we can achieve for exactly this particular probability for each intensity value. We want an approximation, or we can say almost to this particular value, 1 upon L minus 1. So this is what we want to achieve through the histogram equalization. So the main purpose of using histogram equalization is this. So let's see the transformation, how we will do the histogram equalization. So R is any input image intensity values. We apply the transformation T. The output would be small s, where R would take the values from 0 to L minus 1. Now, what are the properties of this particular transformation function T of R that we will be applying so that we get a new intensity values, that is small s. So T or R is, it should be strictly monotonically increasing function. The idea is it should be an increasing function. It should give you a increasing value in the interval 0 to L minus 1. Then for T of R from 0 to L minus 1, it should be also within the range 0 to L minus 1, as R is within the range 0 to L minus 1. Okay. So here we have is, if we have the values, this particular values, single value SQ and we have single value SK. So we want to have a curve which can monotonically increasing curve. This kind of curve we want to achieve, so that for a given RK we can get easily the SK. So T of R should be continuous. It should give you a continuous curve. It should be easily differentiable, because we want a curve which has to be a monotonically increasing curve. Then the probability of S of S should be equal to probability of R, and it should be differentiable with respect to dr upon ds. So let's see through an example how we do this. Suppose we have a 3-bit image. 3-bit image, that means the maximum levels we can have is 2 to the power 3, that is 8. That can be the number of intensity values. The values it can take from 0 to 8 minus 1, that is 0 to 7. That can be the intensity values which the pixels can take over here. So the size of the image is 64 cross 64 pixels. That is the number of pixels. Mn would be equal to 4096. Now this is the distribution Rk, that is input, that is R0. If the 0 is the intensity value, then number of pixels Nk having 0 as the intensity value is 790. Likewise, R1 if equal to 1, if 1 is the intensity value of the pixel, then number of pixels having the intensity value 1 would be 1023. Now we can find the probability of this input, that is PR of Rk, that is Nk upon Mn. Mn is the total number of pixels within the image. So this would be the values that we will be getting. So consecutively we can get for other intensity values also. So for this particular, we calculate the new transformation function, that is T of R0, that is S0, the new intensity value that would give us almost the uniform distribution of the intensity values, would be equal to summation of PR of Rj. This is nothing but what we will do is we will find the cumulative of this. So for the first one it would be 0.19. We will multiply it with the maximum level intensity value, that is L-1, 7. So here S0 would be equal to 7 multiplied by 0.19. This would give me 1.33. Now if we round off this, we will get it equal to 1, because we know the intensity values always take a whole number. They cannot be the decimal, they cannot have a decimal part. Then S1 would be equal to summation. Now at this level what we will do is 0.25 plus the previous one, 0.19. This would be summed and it would be multiplied with the maximum intensity value 7. So we will get S1. So this will be the output that we will get 3.08. If we round off, we get it equal to 3. So likewise we can find for S2, S3, S4, S6 and S7. So nothing but when we have to find S2, we will add this particular value plus 0.21 and multiply the entire summation of this with the 7. When again we go till 0.16, that is we are finding S3, we will sum the initial all values. So if we plot this, this was my initial distribution Rk along the x-axis, then PR of Rk along the y-axis, we get this kind of curve. That is, it's not uniformly distributed. Now if I plot Rk with respect to Sk, we will get this kind of curve. That is, for R0 I am getting 1.4, for 1 I am getting 2.8, likewise. Now if I find the plot for the Sk with respect to probability of S of Sk, you can see that almost we can see distribution is almost equal. It's not exact equal, but it's almost equal. Here it was like lower intensity values have higher distribution, but here we can see that the values are comparatively same. So this is what we achieve through the histogram equalization. Now let's see the next topic of today, that is the spatial filtering. When we talk about the spatial filtering, basically spatial filtering, it consists of a neighborhood around which we can apply and a predefined operation. The linear spatial filtering of an image of size m cross n with a filter of size n cross n is given by this particular expression, where f of x plus s comma y plus t, this is my input image. G of x comma y, this is my image, output image after applying the filter. After applying filter, what we are getting. Okay, let's see through a diagram how we achieve this. Here we have is, for say this is the area around which I want to apply the filter mask. I would be calculating a new value over here. So if I take this particular mask, what we will do is we will superimpose the center of the mask over the pixel for which we want to calculate a new value, g of x comma y. So this all corresponding values would superimpose over this. This would superimpose over this. We are keeping the mask over this particular image. This would superimpose over this. Now what we will do is the values of the mask which are superimposing over the image values, they would be multiplied among each other. That is, we will take the product P of the corresponding values which are superimposed, and then we will do the sum. So this would be, actually we are doing the operation is SOP, sum of products. So we will get a new value that would be put over, that would replace this particular f of x comma y. Likewise, the filter would be moved. On whichever position the filter is being moved, the center would be superimposed at that particular value. So this is called the correlation function operation. So this is denoted by this particular symbol when we do the correlation. Then we have another is the spatial convolution. In the case of convolution, what we do is first we rotate the mask, this particular mask w of x comma y by 180 degree, and then we do the SOP. This is similar to correlation, but the only difference is convolution is nothing but first rotate mask w of x comma y by 180 degree and then apply correlation. So this is what we do, and remember this is the symbol for the convolution. Then smoothing filters. The first filter is basically the box filter. Let's see what the smoothing filter does is, smoothing filters are used for blurring, or we can say basic purpose of the smoothing filter is the noise reduction. We use it for removing the noise. So blurring, in the case of blurring, the small details and the bridging of the small gaps in the line is being removed. So smoothing includes linear filters and non-linear filters. Let's see the linear filter. So linear filter, in the case of the linear filter, we have is a weighted average filter. Weighted average filter is also called the box filter. This is, in the case of the linear filter, what we have is, we have an external mask that is being applied. And the operation we perform is the convolution operation. So here what we do is, we take the multiplication of the values, we do the multiplication and then we do the summation. And then we divide it by the value of all the summation of all the pixel values. So this is the case. This is the average smoothing filter. One is a filter in which all the values of the mask is 1. And then we divide it by 9. 9 is the sum of all these values. This is one of the weighted average filter. It's a very famous filter. Then another is a 1/16 filter. That is, here we have the center as a 4 and its 4 neighbors are 2 and the diagonal neighbors are 1, 1. So we multiply it with the mask. This is a mask filter which is multiplied with the image, and then we divide the value by the 16. That would be put at the center where the center is being superimposed in the image. So these two are the weighted average filters. Let's see how these weighted average filters would give us the result. If we see over here in the first image, this image has a noise. If we take these as a noise, if we do this, if we apply the phases of the weighted average one after the another, that is, on this first we applied the weighted average, we get this result. Then again we applied, we see further it is doing the blurring. It is removing the noise. Further it is removing the noise. Further more noise is being removed. So all the noise from this area has been removed. But the disadvantage is we get a lot of blurring in the case of the weighted average filter. So to overcome this, we have other kind of smoothing filters also. That is the order statistic non-linear filters. These are based upon the ranking of the pixels contained in the filter mask. So here replace the value of the center pixel with the value determined by the ranking result. So in this category we have the filters is a median filter. It's a very good filter if we have to apply the smoothing, that is we have to remove the noise from our image. We can go for the median filters. Then we have the max filter and the mean filter. So let's see the median filter. We know that median is basically what we do is, if I have an image, now for say I want to use the median filter and I want a new value at this particular position. And if I take a 3x3 median filter, we are not applying any external filter. We take the neighborhoods. So we will take this much of area. Now we will rearrange all these values in a ascending order. So 1, 2, 1, 4, 5, 6, 7, 8, 9. Now let's see the middle value. So the middle value over here is 5. So 8 would be replaced by 5. This is how the median filters work. That is based upon the ranking, we arrange the values in a particular order. Here we arrange it in a ascending order and then we replace the value. So if this is an image which is having a noise, we apply, this is a salt pepper noise over here. Here we applied the weighted average filter, averaging filter. That is also of the same kind, 3x3, but it's an external filter. It's removing the noise, but it's getting blurred. This is a result of the median filter. So in comparison to the weighted average filter, median filter is giving us better results. Thank you so much for today's lecture.